In this portion of the lecture, I'm going to talk about the proof of Theorem 8, the invertible matrix theorem. And this material is optional. If you want to skip it, it's fine. And yet, if you're interested in the theory at all, please watch and try to follow along. And so here we go. Let's talk a little bit about the theory. Now, we've already talked about how there are these 1, 2, 3, 4, 5, 6, 7, 8, 9 conditions that are equivalent to each other. By saying they're equivalent, we mean if any one of them is true, they all have to be true. And if any one of them is false, they all have to be false. I've grouped them in groups of 3 because the groups, the relationship between the circled items should seem pretty clear to everybody. It's the connection between the different groups that to me is very subtle here. Also, this only applies to square matrices. So in a lot of the course we talk about matrices that are not square, so none of these equivalences can be considered to hold if we're in a situation where matrices are not square. So let's start talking about the way we would prove this theorem. And what I want to do is, let's see if we can get ABC up there. I'm going to break this proof down into steps. And the first step is to just show the equivalence of A, B, and C. And that's actually not too difficult because we just discussed section 2.2, theorem 7. If you read over the proof of theorem 7 and 2.2, that really is the equivalence of A and B in theorem 8. As far as the equivalence of B and C, that really just comes down to our row reduction algorithm. If a matrix is row equivalent to IN, it's going to have n pivot positions, and vice versa. So I added one little comment here in red. I hope it shows up in the video. You know, if you have n pivot positions and you're a square matrix, that's saying that each column is a pivot column and each row has a pivot position. That sort of goes along with a square matrix having n by n square matrix having n pivot positions. So that's the equivalence of A, B, and C. What about the equivalence of D, E, and F? Well, D and E are equivalent because of, really we showed that back in chapter 1, theorem 11, if you look back at that section. And E and F are equivalent. That was theorem 12 in chapter 1, right near the end of the chapter where we were talking about one-to-one and onto linear transformations. So refer back to those theorems if you want to see why D and E are equivalent and E and F are equivalent. Step 3 is the equivalence of G, H, and I. And let's see if I can get those to appear here on the screen. And really G and H are equivalent because of the definition of onto. That's just what onto means. And H and I are equivalent. That's also theorem 12 in chapter 1. That's the onto portion of that theorem about onto and one-to-one linear transformations. So those are sort of the more straightforward steps in the proof of this theorem. Now it gets a little bit more subtle when we try to show that these separate groups are equivalent to each other. So for me, the next step of the proof would be to show the equivalence of A and D. And so to show that equivalence, first we first prove that A implies D. So statement A is that A is invertible. So assume A is an invertible square matrix, that is A inverse exists. To show that implies D, we have to show that the homogeneous equation has only the trivial solution. So we want to solve the homogeneous equation. If A inverse exists, we can multiply on the left by A inverse for both of those. And then we get INX equals 0, because any matrix times the 0 vector is 0. So we get x equals 0 is the only solution to that homogeneous equation. Thus, A implies D. Next, we want to prove that D implies A, so that if we assume D is true, that the homogeneous equation has only the trivial solution, that implies that A must be invertible. Well, if AX equals 0 has only the trivial solution, let's assume that's true. And what we're going to do is we're going to consider the augmented matrix for that matrix equation. So we're going to have the columns of A followed by a final column of just zeros. That's like the B vector column. And suppose we apply row operations to reduce that augmented matrix. Well, if we only have the trivial solution, then we're going to have to get the identity matrix in those first n columns, because in any other situation we'd either have free variables or no solution. So since there is only one solution, that's what we get. That means A must be row equivalent to the identity matrix, and that actually means that D implies statement B, but we already know that B implies A, so D also implies A. And so that allows us to conclude that A and D are equivalent. Okay. Now, the next part is the trickiest, subtlest part of all this. And I have changed my approach a little bit from the textbook. So if you notice in my statement of the theorem, my theorem doesn't match up exactly to the textbook's version of the theorem, because I was trying to simplify things a little bit. But because I try to simplify things there, here in the statement of the theorem, when we go to prove it, we need some extra help. And I call these extra helping theorems lemmas. And I'm not going to go into the detail of the two lemmas. It's basically, both the lemmas are meant to prove that if you're only able to multiply in one direction, either B times A or A times B, and get the identity matrix, then you got to have inverse. Then the two matrices are inverses of each other. The technical definition of inverse says that, A times A inverse and A inverse times A is the identity. So it is sort of a technical point, and I don't want to dwell on this, but that's the reason why these lemmas are here. And if you really want more information about why I'm writing all that out, you should contact me individually. But the next step of the theorem would be to show the equivalence of statement A and statement G. So, what we're going to do is we're going to take one from the first group and show it's equivalent to one from the third group, and that will tie all those together. We've already shown that A was equivalent to D, so we already tied the first two groups together. Now we got to tie the first group and the third group together. And so I call that the equivalence of A and G. First we show A implies G. Assume A is invertible, A inverse exists. We need to show that the equation AX equals B has a solution for every B. So I let B be any vector in Rn. Can we solve AX equals B? Well, yes, because we can multiply by A inverse on the left. This is not mysterious, this step. And so X equals A inverse B actually is a solution. So that the A implies G direction is not too tricky logically. But now G implies A is the last big step of this proof. And so what we're going to do is we're going to assume that AX equals B has a solution for every B in Rn. And now we're going to work with these E1 through En vectors, those vectors that have a 1 in one entry, zeros elsewhere. They're the columns of the identity matrix, right? The IN matrix. And because AX equals B has a solution for every B, AX equals E1 has a solution, AX equals E2 has a solution, AX equals EN has a solution, all the way down the line. And I'm naming a solution for each one of these separately. So X1 is a solution for the first one, X2 for the second, XN for the last one. And now I claim A inverse exists, and A inverse is actually a matrix that has as its columns this X1, X2 through Xn vector, columns that are the solutions to each one of these separate matrix equations. Now why would that be true? Well, if we take A times this matrix that has columns X1 through Xn, we get a new matrix whose columns are going to be AX1, AX2 through AXN, because that's just one of the properties of matrix multiplication. That's the way the product would look. And because of where X1 through Xn came from, AX1 is E1, AX2 is E2. They're solutions to those equations. So I end up with E1, the product being a matrix with columns E1 through En. That's just the identity matrix. Now, we've shown that if you multiply on one side, you get the identity matrix. Where we need the lemmas is, why does that imply that if we multiply the other way around, we also get the identity matrix? So that's a little bit subtle logic there that I think is you'd have to talk to me about if you wanted to really get it down. But so that's why this does give us G implies A. So A and G are equivalent. And so from the preceding steps, we see that A, B, C, D, E, F, G, H, I are all equivalent to each other. And that's the end of the proof of Theorem 8.